This is Coding Math, episode 58, Array Math. I wanted to take a bit of time to cover some tips and tricks for working with arrays, particularly a few that are at least somewhat math-related. Before we get into the tricks, let's quickly cover the basics of arrays just to ensure that we're all on the same page. So we'll start off kind of slow with some stuff you probably already know, but bear with it and we'll get into some pretty cool stuff. An array is a collection of values that are stored in a single object. The thing that distinguishes arrays from other collection types is that each element is accessible by a numerical index. And because you're using numbers, this lets you use various mathematical algorithms to access and manipulate the array. Now, arrays are implemented differently in different languages, and there are different types of structures that fall under the heading array. In some of these, an array can only hold a single type of data. So if you make a string array, you can only store a string in it. If you try to store a number or some other type of value in that array, you're going to get an error. In other languages, though, such as JavaScript, an array can hold multiple types of objects. So one element could hold a string, the next could be a number, and another some other kind of object. Now, in some array constructs, you need to use special methods to access specific elements of an array, such as array.get3 to get the element located in index 3. And other methods like put or set or insert to set the value of an element at a particular index. For example, array set 3 foo. While JavaScript arrays do have various methods for manipulating elements, you can get or set individual elements with the square bracket syntax. So array 3 equals foo to set an element, or value equals array 3 to get an element. Some languages also have shortcuts for creating arrays with predetermined values. In JavaScript, you can create an array by saying new array, or just set up a comma delimited list of values inside a pair of square brackets. In fact, you can create a new empty array by typing a pair of square brackets with nothing in between. One last important point is that for most implementations, arrays are zero-indexed. That means that the first element is element 0, and the index of the last element is equal to the number of elements in the array, or its length, minus 1. So if you have an array of 10 elements, they will be indexed as 0 to 9. Now, one of the most common things to do with arrays is to loop through them, accessing each of the elements in order. The traditional way to do this is with a for loop. Let's take a quick look at the structure of a for loop. In the parentheses are 3 blocks. These are sometimes known as the initialization block, the condition, and the afterthought. The initialization is executed at the start of the first execution of the loop. The condition is checked before each iteration. If it evaluates to true, the code in the main body of the for loop is run. When that's done, the afterthought block is run. The condition is then checked again, and that cycle continues until the condition evaluates to false, in which case the for loop exits. Now, 99% of the for loops you'll see will use the initialization to create a variable and set it to 0. The condition will check if that variable is less than a certain value, usually the length of an array. And the afterthought increments the variable by 1. Inside of the for loop, you get the element from the array that corresponds to that variable's current value, and do something with that element. So here's our first so-called trick. It's one I'm sure you probably already know because people complain when I don't do it here. In this example, we're using array length as the condition. Since in most cases this value is not going to change, we can read this value once before the for loop and save it in a variable, say, called len, and use that variable in the condition block. In fact, we can even move this into the initialization block. You probably know that you can define multiple variables with a single var statement, separating each var with a comma. So we can just say var I equals 0, comma, len equals array length. This is nice because it includes all the necessary for loop code in the for loop itself. If you were to refactor and move that for loop somewhere else, there's no way to forget to move the len variable along with it. Now, theoretically, accessing a simple variable is going to be faster than accessing the length property of an array, which internally may be some kind of getter function. And in the past, this was definitely a valid optimization. However, since most modern JavaScript engines will do internal optimization on code like this, you'll find that there's no actual benefit to this quote-unquote optimization. In fact, I created a test that iterates over an array containing 10 million random numbers and adds them up. On my machine, on both Firefox and Chrome, both techniques take around 18 milliseconds on average. Sometimes one is a millisecond or so faster than the other, sometimes the opposite. A lot of the time, they're dead even. You may get different results in different browsers or platforms, but even if you get a difference, I'm betting that for most modern browsers, it's going to be negligible. So this technique of saving the length variable, it's not a bad habit, and there's certainly no downside to it, but don't think that it's some magic trick that's going to make your code run faster, or that if you don't do it, your code is going to grind to a halt. Also, don't believe me. Run your own tests. If you find something drastically different, I'd like to see it. Next, let's look at alternate methods of looping through arrays. In addition to for loops, you can use a while loop. This amounts to the same thing, but you have to set the parameters up manually. A while loop just gives you the condition block. If the condition evaluates to true, it runs the main code block and reevaluates the condition continuously until it evaluates to false. So, to loop through an array, you need to set up an iterator variable outside the loop. Check it in the condition and increment it somewhere in the loop, usually right before the end. Lately, functional reactive programming has come more and more into popularity. In that paradigm, you could use a function like for_each, which is now built into the JavaScript array object. This lets you define a function that will be called for each element of the array, passing in each element as a parameter. This hides the internal mechanics from you, allowing you to focus on what you want to happen with the elements, and not worry about how the iteration is happening. One thing to note, though, is that while this type of programming definitely has its benefits, performance is not one of them. In the 10 million element test I described earlier, where the for loops were taking around 18 milliseconds each, array for each was taking over 400 milliseconds, many times slower. So in any kind of application with large loops where performance is vital, you're going to want to stick with old-fashioned loops. An alternate method of looping through arrays is to go in reverse. With a for loop, we would initialize I to array length -1, so it points to the last item of the array. Then we make the condition I greater than or equal to 0, so that it goes all the way down to the first item, 0. Finally, we set the afterthought to decrement I by 1 rather than increment it. You should be able to figure out how to do this with a while loop as well. So why would you want to go backwards? Well, you might hear people claiming that the fastest way to iterate over a list is a reverse while loop. This might be true in certain languages, on certain systems. I'm not going to make any claims about it for JavaScript, but I suspect any optimization here would be minimal. One valid use of backwards looping is if you're removing items from a list while iterating over it. Some languages don't actually allow you to do this, but JavaScript does, and you can get into trouble if you don't do it right. Let me change this list so we have 2 5s in here. Now say I want to remove all the 5s from this array. I'll set up the for loop to go forward again. And inside that, I'll check if array I equals 5. If so, I'll use array splice I1 to remove that element. The splice method removes a given number of elements starting at a given index. We're saying remove one element starting at I. Okay, so we loop through and we hit the first 5 at index 2 and we remove it. But when we do that, all the remaining elements shift down. So the next 5 in the list is now at index 2. But now we hit the afterthought block, which increments I by 1, and then we're checking index 3. That second 5 slipped right by us. And you can see it's still in the array. Now there are ways to handle this by messing with the I variable within the main block of the for loop. I personally don't like doing that. I think it can cause some confusion when the I variable is changing outside those 3 initial blocks. So if I set this loop back to reverse, we start from the end and move back, find the second 5 at index 3, remove it, move to index 2, find that first 5, remove it, and all is good. Okay, getting back to more math-related items. Another common array application is the creation of a 2-dimensional array. This is basically an array where each element in the array is another array. This is best visualized as a grid, and in fact, that's how it's often used. Here, the columns are the elements of the initial array 0 through 4, and the rows are the indexes into the secondary arrays, also 0 to 4. This element here could be indexed as element 3 of the first array, and within that, element 1 of that subarray. In this case, you need to decide how many columns you want and go through and create the subarrays for each of those top elements. So we'll loop through from, say, 0 to 9 to create 10 columns. And for each column, we'll say grid I equals square brackets to create a new array there. Now you can access, say, the third column of the grid with grid 2. This gives you the array that is stored there. You can then specify which row you want with another set of square brackets, say grid 2, 3. Now this works just fine, but in many languages, the very act of accessing an individual array element can be rather slow. When you access an array element to get back another array and then have to access another element from that array, you're compounding the problem. So here's a little trick to make a single-dimensional array function like a two-dimensional one. In this case, you have one large array with all of the elements stored sequentially. I'll set this up to look like a grid just so you can get the idea, but remember, this is just a single array. So here we have elements 0 to 4 as the first row of the grid. Elements 5 through 9 are the second row, 10 to 14 are the third row, and so on. Now say we want to access this element here. That's column 3, row 2. You can also count up and see that it's actually simply element 13 in the array. The formula for getting the index from the row and column is the row number times the number of columns plus the column number. Here that means row 2 times 5 columns per row plus column 3, which is 13. Let's see this in action. I'll get rid of all this and set a variable numCalls to 10. Now I can create a function called get that takes parameters of call and row. And that we can return grid row times number of columns plus call. Then another function called set, also accepting call and row, plus value. This one says grid row times numCalls plus call equals value. Of course, you probably want to create some kind of class or object or module that encapsulates all this. So now I can say set 4, 5, hello world. And check that by saying something like console log get 4, 5. Check the console, and yes, what we logged is what we saved in the grid. Now, one place you'll see this in action is how HTML5's canvas stores pixel values. On the 2D rendering context, there are two methods, getImageData and setImageData. GetImageData returns a special object. That object has a property called data that contains all of the pixel information for the canvas, or the portion of the canvas you asked for. That data property is an array, but it's not as simple as a 1 pixel per element array. The pixel data is stored as separate elements for each red, green, blue, and alpha channel of each pixel. So the first 4 values in the array are the red, green, blue, and alpha channels of pixel 0, 0. The next 4 elements are the R, G, B, and A of pixel 1, 0, and so on across each row and down each column of pixels. So to get the index of a particular pixel, we need to multiply the Y value of the pixel we want by the width of the rectangular pixel area plus the X value. Just consider X and Y as columns and rows in a grid of pixels, and the width is the number of columns. But here, because each pixel takes up 4 elements, we then need to multiply the whole thing by 4. And that gets us to the beginning of the block of 4 elements that define a single pixel. That index will be the red channel. Index plus 1 will be the green channel, index plus 2 is the blue, and plus 3 is the alpha channel. It's also worth noting that the image data object has properties for the width and height of the canvas area that was captured, so we can use that width value in our calculation. With this, we can make the worst color chooser in the world. Here I've set up a 200 by 200 canvas, a bit of CSS, and in the code I've gone through and filled it with 20 by 20 blocks, each containing a random color. At some point I'll do an episode on color, but for now just roll with it. Then we can get the image data for the canvas. We just call context getImageData, passing in the XY width and height of the area of pixels we want to get. Now we can set up a mouse move listener. This will get the current XY value of the mouse. In the CSS, I've removed any margins or paddings so the canvas sits exactly at 0, 0. If you don't do that, you'll have to convert the event client X and Y values to the local coordinates. Here they line up exactly. I'm going to call a function getPixel, passing in X and Y. We'll create that function in a moment. This will return a color value, so we can just assign that to document, body, style, background color, which should change the color of the background of the page. Now that getPixel function. Again, it takes X and Y. We'll do our XY to index calculation here. It's Y times image data width plus X. And remember, we need to multiply this all times 4. Now we have the index to the first channel of the given pixel. That's our red value, so we can say red equals image data, data, index. And we can get the green channel with index plus 1, blue with index plus 2, and alpha index plus 3. Here, alpha will come in as a value in the range from 0 to 255, but we'll need it as a float between 0 and 1. Simply dividing it by 255 will give us just that. Now we can use those 4 values to construct an RGBA string. We start with RGBA parentheses, then add on a red, comma, green, comma, blue, comma, and alpha. And finally, close the parentheses and return that string. Should be all set. Now as we mouse over any of these blocks, the background color changes to that color. Of course, you can make a much more usable set of color swatches or even figure out how to get an image in there. Okay, one more trick I want to show you on arrays, and that's the case where you want to compare every element in an array to every other element. This might be useful in a case where you have a particle system and you want all the particles to react to each other, or set up a collision detection between all of the objects in an array. For this example, I'm going to partially recreate a piece I did years ago that was based on a piece that Jared Tarbell did called Node Garden. In my take on the node garden, you have a bunch of nodes. These are just two-dimensional points. You measure the distance between every pair of points, and if they're within a certain maximum distance, you connect them with a line. This requires comparing every single node to every single other node in the system. We'll start fresh with a canvas that's 600 by 600. I'll create an array called nodes and loop through it 100 times. In each iteration, I'll push a new random point onto the nodes array. X and Y will both be math random times 600. Now, just to prove that the nodes are set up, I'll make them visible. I'll loop through again and draw a 2-pixel radius circle on each node. And there they are. Now we need to compare them all to each other and calculate the distance between each and every pair. Well, we know that we need to loop through one time to get the first node to compare. So we'll say for var I equals 0, I less than node's length, I++. And immediately we get a reference to that first node, nodes I, calling that node A. Now we need to compare node I to every other node. So we set up an inner loop with j. For var j equals 0, j is less than node's length, j++. And get a reference to node j, making that node B. Then I'll set a variable called maxDist and make that 100 for now. Any pair of nodes that are less than maxDist will get connected by a line. So we get a distance between node A and B on the x-axis and the y-axis, and use a square root to get the overall distance. And if the distance is less than maxDist, we begin a path, move to node AX, node AY, line to node BX, node BY, and stroke that path. We run that, and there's our node garden, and it looks half decent. But there are some serious problems with the code here. You may and may not be able to see it, but those lines are a lot darker than they really should be. That's because they're all being drawn twice. In fact, this code is doing more than double the work it should be doing. Let's walk through it. Say we have 5 nodes, 0 through 4. We run through comparing 0 to all the rest. Well, we already see the first problem here. We're comparing node 0 to node 0. This is totally unnecessary for our purposes. And the same thing will happen for nodes 1, 2, and all the rest. We could throw an if statement in there to prevent the comparison of the same node. It's not pretty, but it will solve that situation. So let's assume we did that and carry on with the flow. Okay, node 0 has been checked against 1, 2, 3, and 4. We move on to the next iteration of the first loop, and we're looking at node 1. We compare it to all the others. But wait, we already checked node 0 against node 1. What's the use of checking node 1 against node 0? They're the same two nodes. They're the same distance apart no matter which order you check them in. So we wind up drawing that line twice, which is why it looks so dark. When we get to node 2, we check it against everything else. But again, we've done even more duplicate work. So let's look at what we should be doing. We compare node 0 to 1, 2, 3, and 4. Note that we've skipped 0 to 0 comparison. Then we start with 1. It's already been compared to 0, and we don't need to compare it to itself, so it gets checked against 2, 3, and 4. Node 2 only needs to be checked against 3 and 4, and when we get to 3, it only needs to be checked against 4. We don't need to do anything with node 4 since everything has already been checked with it. So assuming I is the first index and j is the second one, the j loop should start at I plus 1 and go up to array length. Back in the code, all we need to do is change the second loop from var j equals 0 to var j equals I plus 1. This will skip over all the nodes that have already been checked and also avoid checking any nodes against themselves. This is great, but we need to adjust one more thing. Remember that when we hit the last element, it's already been checked against all the others. So we can cut short the first loop. Instead of going from 0 to node's length, we can say 0 to node's length minus 1. This code is more than twice as efficient as the first version, and actually looks better because all the lines are drawn only once. There's another fun thing you can do here, which is to vary the line width based on the distance. If we divide dist by max dist, we get values from 0 to 1, and if we subtract that from 1, we get a neat effect. Nodes that are far apart are connected by very thin lines, as if the lines have been stretched out. Try changing the max dist value to get very different effects. Also, try animating this one. If you do it right, it's really beautiful. Okay, the whole last part of this was a bit beyond array math, but I like to give you something fun to play around with, in addition to useful techniques. Hope you enjoy that.